Now, on this molecule with the alcohol, you have a really strong difference in electronegativity here. So you see a really strong patch of red and a really strong patch of blue. If you should happen to have a molecule that's not so obvious, okay, so for example, I think we had something, I think somebody built this the other day, dichloromethane, okay, minimize the energy. I'm going to do the calculations. So I'm going to go to PM3, leave this equilibrium geometry, everything else is fine, submit. Okay, I'm going to display that electrostatic potential map. Whoops, completed, okay. Okay, now you can see here that there's not a whole lot of strong dipoles. There's maybe more green and yellow over here than there would be, but it's kind of hard to tell what the dipole might be. Let's display the dipole also so we can actually see what we're looking at. In order to display properties and actually see that dipole moment, you need to deselect the surface. So I go display dipole vector. Okay, so you can see that there's a positive charge here on the top, which should be more blue on the electrostatic map because the hydrogens would be less electronegative than carbon or chlorine. Chlorine is going to be pulling electron density away from the carbon, and so these should be more red down here. But you can see that the colors are really muted, and it's actually kind of hard to tell just from the electrostatic potential map where that charge might be. And so what we can do, if you don't need to compare this to other molecules, if you select the surface and then go to display properties, okay, you'll notice that that dipole number isn't there anymore because we've selected the surface. Up here gives us the color range. So right now the default always is just set to a -200 to 200. Red is a -200, blue is a +200, and if your minimum and maximum charge values on your electrostatic potential map are less than that, okay, we're working from -76 to 84, so we're really working in this range here from yellow to like teal. Okay, so it's hard to see really good differences there, or to tell the difference between where electron rich and electron poor is. This is a good indicator from molecule to molecule, the strength of that dipole, okay? But if you just need to look within one molecule, then you can reset this maximum and minimum value for the color scale so that you can really tell it's exaggerated where that electron density is. So I'm going to reset this. So now my maximum and my minimum match on my color scale. And now you can see it's really obvious, okay, that my electron density here is around or in between the chlorine atoms, which is where that dipole is pointing towards, and it's pointing away from the blue end, which is the electron deficient end. Okay, so I'm going to go back to those display properties and reset that to the standard default settings so that you can see how different that is, right? And not only that, now as long as they're on the same scale, you can really compare the methanol to the methylene chloride, right? So if we go to methanol and we look at the magnitude of the dipole, our dipole moment here is 1.49 dBi, okay? And if we go to methylene chloride and look at the dipole moment, we have 1.36. Okay, so the dipole moment here, 1.36, is telling us about the difference, right, for the whole molecule. What does that spread in electron density look like? And they're not too different, right? But the difference here between carbon and chlorine is not that different than oxygen and hydrogen. And so the localized dipoles look a lot different in methanol here, right, than they would for methylene chloride.